In this video, we're going to learn a cool way to look at differential equations. It's called a slope field. And so in a slope field, what we're going to look at is a differential equation. Let's say we have dy dx equals x squared, for example. And so what we're going to do is we're going to plot a graph. And now, instead of plotting like a function, like a parabola that is y equals x squared, we're going to plot the slopes. This is a derivative. Remember that a derivative is a slope, and so we're going to plot the slopes at different points. So for example, at 0, 0, what we do to find the slope is we plug in these points into the formula. Well, the x value is 0, so I'm going to get 0 squared, which is 0. So at 0, 0, the slope is 0, and the way I denote that is by using a little line that has that slope. So I drew a little line with a slope of 0. Notice that really any point on this graph with an x-coordinate of 0 will give you a slope of 0. So anywhere along the y-axis, we have a slope of 0, just like that. Very nice. Okay, let's take a look at what happens if I'm not on the y-axis. Let's say I'm at the point here at 1, comma 0. What I do to find the slope, I take my point and I plug it into my equation. 1 squared is 1, and so my slope is 1, so therefore I draw a little line with a slope of 1. And that's going to be true for any point with an x value of 1, so it looks like that. It's also going to be true if my x value is negative 1, because if I plug in negative 1 into x squared, I'm going to get positive 1 as well. And so on the other side, at x equals negative 1, I'm going to have slopes of positive 1 like this. And so these are going to be my slopes. And this pattern continues. So if x equals 2, my slopes will be a positive 2, which is a little bit steeper. Now, these are not going to be exact, so you kind of just estimate, like, okay, this is steeper, and then it's going to be even steeper as we keep going along like this. So on the other side, at negative 2, we're going to have slopes that are about 2, so steeper than 1, like this, and then same thing going down, and then like that. Okay, and what this is a slope field, because this tells us what the slopes of this differential equation look like. Now, you can imagine this has lots of practical applications. For example, wind. Wind moves in a somewhat random pattern, but you can model wind using slope fields and say, like, okay, if I put a particle here, which way is it going to go? Well, here it's going to follow this path that's like following the slopes, but then it's going to curve upwards because it's going to follow the slopes like this, and it's going to go up and up and up like that. And going the other way, it's going to go down like this. And so what slope fields allow us to do, they allow us to draw a solution curve just based on the way that the slopes are going. So this could be the wind and how a particle reacts in the wind, or these could be currents in your bathtub, and so if you put a little rubber ducky here, which way is it going to go in your bathtub based on the water currents and that sort of thing. So slope fields have lots of practical applications. We're not going to look at a lot of them. We're just going to kind of tool around with how do you draw them and that sort of thing. Let's look at a more complicated one, and let's try to draw it again. So let's say that dy dx is x plus y. Ooh, interesting. Alright, so we have the differential equation x plus y. We're going to look at some points. So we're going to look at 0, 0. We'll look at 1, 0, 1, 1, negative 1, 0, negative 1, 1. We'll look at negative 1, negative 1. Oops, we'll look at 1, negative 1, and 0, negative 1. This might be all of them. It might not be. Anyway, so let's find the slope at each of these points. So at 0, 0, to find the slope, I plug it in. So 0 plus 0 is 0. I take this 0, and at that point, I draw a little thing with a slope of 0. Cool. At 1, comma 0, I plug it in. 1 plus 0 is 1. You get the idea. And so this has a slope of 1. 1, comma 1, I get 2. So that's over here, and I get a steeper slope. Negative 1, comma 0, I'm going to get negative 1. So that's going to look like that. At negative 1, 1, I get 0, so flat. This is going to be negative 2. Oops. I messed up. I need to go back. This one here, this is 0. This should really be up here at -1, 1. I swear I know how to plot points. -1, -1, this is going to be -2. That's down here, like that. 0, -1 will be -1 as well, so like that. 1, -1 will be 0, so that's here. And then I missed one, it was 0, comma 1. This is going to have a slope of 1, so like that. So it's going to be a kind of weird graph. I'm going to fill out the rest of this because I know what this looks like. There's a pattern here. These are all going to be 0 slopes, and then these are all going to kind of shoot away like this. This is going to be the same, and then these are going to shoot away like this. I know what it looks like because I've done this before. But you get this as your slope field. And so what happens is, let's say that I'm plotting a solution. So I'm going to start at 0, 0. And to plot the solution, I follow the slope curve. So I'm going to go straight horizontal, and then it's going to kind of shoot up and follow these curves away. And same thing going back, I'm going to follow this curve. And actually, this is going to end up going along the path like this. So you kind of, as you practice, you get a general sense for how to draw solutions. This is an approximate solution curve. It's not exact at all because we actually didn't solve anything. But it's a good way to visualize what solutions would look like. One last quick thing. In that first example, we had the differential equation dy dx equals x squared. We can actually solve this by using separation and integration. Let's go ahead and do our colors. So dy dx equals x squared. Alright, I need to separate and integrate. I can only use multiplication or division. So I'm going to take the dx and multiply it to the other side. So I'm going to get dy equals x squared dx. Great, now the variables are separated, so I'm going to integrate both sides. I get y plus c1 equals the integral of x cubed, x squared is going to be x cubed over 3. I have a c2, and then I solve for y. And so y is going to be equal to x cubed over 3. And then remember, when you combine the two constants, you just get a general constant, which is c. This is my general solution, if you remember that from the, it's my general solution from the Intro to Differential Equations video. And now notice that this is a cubic, and the plus c, if you remember your transformations, is a vertical shift based on what the initial condition is. So let's go ahead and look at the slope field for that. Oh hey, there it is. Notice, first of all, that the solution that we plotted was a cubic. Oh my gosh, that's really cool because that's what our solution tells us it should be. Furthermore, depending upon where we start the graph, let's say we started it down here, we get the same shape, it's just changed by a vertical shift. And so that's the purpose of that c value, the plus c, is based on the initial condition, we tell the function where it starts. And so that's the purpose of c when you're graphing solutions to differential equations.